So this leads into the methodology for graphical convolution. And there are a number of steps involved in calculating it by hand. The first thing I recommend is get some good graph paper, because you're going to want to graph things one on top of each other, the other, or directly underneath each other, and you do not want to lose track of their overlap vertically. So you're going to want to have graph paper to keep track of their overlap. So we're going to graph x of tau, and there should be an h of tau here, but we're going to graph x of tau and h of tau, and from those two we're going to choose which one to flip and shift. So this is one thing I didn't mention here. It's not super important, but it doesn't matter which function you choose here to do a reversal and shift, because you'll end up with the same value. And we can demonstrate that at some point if you want, but just take it for granted right now. And it's usually easiest to choose the simplest function. And we're going to do an example, and you'll see. So we're going to flip and shift that and graph it. So now we should have two graphs, one of x, one of h of t minus tau. And remember that we're going to want to graph them as a function of tau. Okay? And then we're going to want to identify the transition points on each of those and label them. And we're going to draw vertical lines at those to establish different regions, and then label the graphs with functional form in each region. We'll see an example of that in a second. I'll explain what I mean by transition points with those. And then as basically h of whatever signal is flipped, in this case we'll just say it's h, you have to imagine that it is as far towards infinity as possible. And then as we increase t, there's going to be a separate case that we need to consider whenever there's a transition from one transition line crosses over another transition line. For each of those, we're going to have to redraw the graphs, determine the integrand, identify the limits, and solve the integral. Messy, I know. Okay. So, as an example, let's assume we have a system which has a unit step function as the impulse response, and then we are going to ask for the output of the system when the input looks like this. So note that this is two unit step functions, and it's actually a pulse, and this is some sort of ramp that is shifted and actually has a negative slope. So if we graph those, they will look like that. Okay? And now we're going to choose which function to flip and shift. Generally we want to choose the simpler function. So this looks like it's simpler to deal with than that ramp. So we're going to flip h. Okay. So first off, we want to find the flipped version of h. So first, and remember it's in terms of tau. Okay, so here's h of tau. This is h of minus tau, and then this is h of t minus tau. Remember, that's effectively plus t, so it's shifted to the left. Okay. Now we're going to graph both x and h of t minus tau, and we're going to identify transition points. So this is what I mean by transition points, that this function basically has a certain value in this region, and then there's a transition to a different functional form. In this case, it's just flat. And then another transition into another functional form. And we're going to label the functional form in those regions up above. So we know that in this region, the function is 0. In this region, the function is 1. And in the rest, it's equal to 0. For x of tau, it's equal to 0 in this region. It's equal to minus 2 times, I should say tau minus 1 here actually, in this region. And then it's equal to 0 in the third region. Okay? then, like I said, we're going to have a separate case existing whenever that we have a transition as we move. So remember that H, the blue line, is going to be shifting forward, shifting to the right as we increase tau, or sorry, as we increase t. And so these lines will all of a sudden cross over each other, and that indicates that we're going to have a different case to deal with. Okay, so this is our first case, when the two functions do not overlap at all. And note that for the red curve, x of tau, I've written down the functional forms in each of the regions, not just for x, but also for tau. So it's 0 in this part of tau, it's 0 in this part of tau, or sorry, 0 in this part of h, 0 in this part of h, 0 in this part of h. It's minus 2 times tau minus 1 in here, and 0. And then h of t minus tau in the 5 different areas, I write those down as well. And then this is what is under the integral. And how do we find that? We just multiply upwards. So 0 times 0 gives us 0. This minus 2 tau minus 1 times 0 is still 0. So you'll notice that everywhere it is 0. So that shouldn't contribute anything. When I multiply these two graphs together, I'm just going to get a flat line. But let's take a look at it exactly and notice that I've broken this up into 5 pieces, one for each of these zones here. And I'm looking at the integral from minus infinity to t minus 2, and then t minus 2 to t, and then t to 0, 0 to 1, and 1 to infinity. So I've got all 5 of those integrals, but in this case we have 0, 0, 0, 0, and 0, and so the total is 0. And so for the output, for any t less than 0, the output is going to be 0. Okay, so now notice that, so this is where I've shifted this blue curve to the right, and now this blue line has actually crossed over here. So I still have 5 different regions, 1, 2, 3, 4, 5, and I'm going to do the same thing. I'm going to write down the values of x. Note they haven't changed. And I'm going to write down the values of h in those regions, and I'm going to multiply upwards. And note there's only one region that's non-zero. Okay, and that region extends from 0 to t. Okay, so it's only going to be this one that contributes anything. Okay? And if we do those calculations, we're going to get this functional form. And so that case is going to exist as soon as t becomes 0, and it's going to keep going until this line gets to, this blue line gets to here, and that's when t equals 1. So it's happening for t going from 0 to 1. As I keep moving to the right, now I cross over. Okay, and I've still got my 5 regions. I'm going to multiply upwards, and this time the functional form looks like that, but now the limits of that zone are different. So they are going to go from 0 to 1. Okay, because this is going to contribute nothing, and this is going to contribute nothing. So we're just going from 0 to 1. And that's indicated right there. We calculate it, we get a value of 1. And that's the region where that is happening. So that is going to happen until this blue line gets to here. Okay, so you have to look at both of them and whether they're crossing something. So that's going to happen. It's going to be 1 until this blue line gets to here, and that's when t minus 2 equals 0. And that would be when t equals 2. So that's why we've indicated that region there. Okay. Let's just see if we, yeah. So then that trailing edge gets into the triangle, and now we have just this region in here which has a non-zero functional form, and that is from t minus 2 to 1. So that's this guy right here. And if you solve all of that, you will get that. Okay? And that is going to last until this blue line gets to here. That's when t minus 2 equals 1, or in other words, when t equals 3. And now we're in the last case, and that's where t is greater than 3. There's no longer any overlap, so we just get 0. And if you were to graph that, and you could do that in MATLAB or whatever, that's kind of a pig to actually do by hand. But we have some sort of quadratic, although it's an inverted quadratic, so it's actually like a parabola that's not finished, an inverted parabola that's not finished. And then it's constant, then it's the upright parabola, and then 0. Okay? All right, so now we're going to look at some properties of convolution. And it's important to realize that we need to be able to distinguish between convolution and multiplication, and you need to indicate clearly when you're writing things down that it's an asterisk for convolution and an X for multiplication. So remember that multiplication of a function with an impulse still gives us a function which is an impulse scaled by an amplitude. Okay, and this is just another way of if we had shifted x instead of the delta function, but that's okay. So first off, for convolution, it doesn't matter what order you write the functions, and that's what's called the commutative property. So really it's just saying these two integrals are equal, and that's what I was saying. It doesn't matter which function you choose to do the shift. And I'm not going to prove it, just take it for granted. The next one is the shifting property. This is probably the most important one to us as electrical engineers, let alone everyone. And we'll see why in quite a while, but it's really, really important. This is really the only time that you want to do convolution in reality, and that's when you are convolving with an impulse. And the idea is that if you convolve any function with delta of t, you just get that function again. I want you to think of this graphically. So we have f of t convolved with an impulse at the origin, we get f of t. What's more important is if we put a shift on that impulse, what you will actually get is a shifted version of that function. Okay, so if this was the original function, we've convolved it with this impulse up here. What you do is you take this graph and you now just center it at t naught. And so you get that. Very, very important property. Next is the associative property, and that is just that it doesn't matter what order you do two consecutive convolutions. It's the same with multiplication, so if you have three numbers, multiply them together, it doesn't matter what order you do it. Same thing is true of convolution. And what that means is, if I have, think of this as representing a signal going into a first system, and then that is the input to the next system, like here. That is, because it's associative, it can be written down like that, where we take those two systems and combine them and then put the input in, or reverse the order of the convolutions before we put it in, or we could even reverse the order of the systems before we get it in. All of these four systems are equivalent to each other. The only reason that's true is because they're linear and time invariant. Okay, and then the distributive property, which is multiplication with addition, just that you can, just like with multiplication, you can distribute this convolution into the first term plus the second term. And so if we have a system which can be represented as an one impulse response plus another, then that's the same as a branch and then an add. That's really just representing that right-hand side. Both of those systems are equivalent. As an example, let's take a look at trying to find with all those properties, let's try and find the impulse response of the system below. So what we want to do is have basically a single system which represents this entire system. And I am going to go to OneNote to do that. Okay, so we have this complicated system, and as long as we know that each of the components is linear and time invariant, then we can use all of those convolution properties and simplify this. So we can take a look at x going in here. So on the output, we should have x convolved with h1. Here we should have x convolved with h2. And then if I add them together, then I have x convolved with h1 plus h2. And then here on the bottom, I've got x going in, and I have x convolved with h4. And then here, I'm going to have x convolved with h1 plus h2. And that whole thing is input into h3, so I can just put a convolution with h3 there. And then those two signals are added together, so at our output, we have that plus that. And now what I want to do is take that whole thing, factor out the x of t, and there we go. And so this is basically the impulse response of the entire system. And sorry, I forgot. I'm just going to erase that. I should have x of t convolved with that. So this is basically the impulse response of the entire system. Okay, so if we had the impulse response of each individual system, then we could actually calculate this before we do our convolution. That's basically the end of that is the end of the section on impulse response and convolution, and you are going to get a whole lot of practice dealing with this. So if it didn't sink in yet, that's okay. We're going to get lots of practice with it, and hopefully as you move through that, it will sink in. Thanks.